Okay, this test is to see if there's any change within our coil or L1 when I switch from the battery and send the charge back to the circuit, the input of the circuit should I say, which of course is on the positive side of this cap. This amp meter here is coming from the LED, which would normally be switched straight into our cap, but in this case we're going through our amp meter then into the cap. So that's going to tell us our current is being returned back to the system from our inductive kickback of the coil. The battery, unlike all the others, is negative onto the negative rail and not positive onto the negative rail, or negative onto the positive rail, sorry. So it is a parallel connection, not a series connection, which you can't do with the standard pulse motor circuit, otherwise you get smoke, and I know this because I've tried it many times. If you don't get smoke, then that will simply stop. Okay, our coil, I wound a new one today, very roughly. Of course we have our L1 and L2 coils here, but I normally put a little indicator coil on first, wind a little indicator coil on first on most of my coils, and this is so I can hook the scope up to it and watch any changes within the coil while making adjustments to the system. It means that it is also ground isolated and we have no trouble. What I've done in this case is run it through a full wave bridge rectifier and a cap, which is a 1000 microfarad I believe, 25 volts, no 2200 microfarads, okay. So we've rectified it, smoothed it out, and I have a 1.5 k ohm resistor across the cap to bleed it down. This is so we can monitor any changes when we switch from the battery back into the circuit with our return, and just to make sure nothing happens, the power in the coil doesn't change. Okay, so our cap voltage is 7.84 volts and we are putting 257 milliamps at 12 volts into the system at the moment. The two consumptions, if you want to call it that, of the power in would be our transistor and of course L1. Now the transistor switching power is produced by L2 and the magnets in the rotor spinning past it, and that's creating our switching current for the transistor. The flywheel or the rotor is sitting on about 2100 RPMs and it remains stable throughout switching, which is a good indication that nothing is changing within the coil when we switch it over. This meter here is the amp meter. It's hooked between the output of the LED and our input back into the positive side of our circuit. So our inductive return will be going through this amp meter, so we'll be able to measure how much we're getting back from our coil and dumping back into the system. At the moment it is hooked up to a battery. Unlike other pulse circuits, the negative of the battery is hooked to the negative rail of the circuit, which is common throughout the whole circuit. Okay, so like I said, 258 milliamps at our 12 volts, and guess what, there's no adjustment from calibration trim pots for the milliamp reading on the power supply, so we're stuck with about 9 to 11 milliamps short. It's not really bothering me because I always use the meters anyway. Okay, so this one has gone off for some reason. I don't know why. There's no buzzing or anything. That was after we found out how to disable the auto shut off. It's just quite amazing what you can find in the manual. Alright, so we're going to switch it over. 7.84 volts in our little cap at the moment. 257 milliamps at 12 volts going into the system. You probably didn't see that, but the LED has gone a little brighter. I could see that simply by the reflection on the wall. Our input current from our power supply now is 125 milliamps at 12 volts. So as you can see, the voltage across our little cap hasn't changed. It is still settling down a little bit. Not quite sure where we get that big surge when I switch it over, but we do. But the system settles back in to what it was before. So that's telling me there's no change as far as power output from our coil is going, and of course the RPMs remain the same because I've done this test many times. So here's the interesting thing. Our power supply is now supplying 123-24 milliamps at 12 volts. An inductive return back into C1 is supplying 164 milliamps at 12 volts. So I found that quite interesting. The return from the coil is actually higher than the input required from the power supply. So that's this test done. And next I'm just going to do a plain Jane efficiency test just to see how much efficiency we get charging the battery. Decent pulse motor might give you 50% back into the charged battery, most around 35 to 40%. So we'll see how this one stacks up. Okay, in this part of the video we're just going to have a look at the efficiency of the charging side of it. As far as charging batteries, 173 milliamps at our 12 volts is our input, 172, 173, as can be seen here as well. I should mention that meter there is hooked between C1 and C2. And they're both reading the same, of course, because they are in series. Our output to our battery is 121 milliamps at 12.52 volts, which is what our battery is at the moment. Also, of course, getting desulfated. That was actually a cactus battery, and it's managed to bring it back quite good. So our charge input to our battery, that is our input to the system. The other thing is I've changed back to the larger coil. It's simply more efficient because it doesn't have the small coil in there that is basically loaded across that capacitor and resistor. Now there was one other thing I needed to point out with this system is, I'll switch it over and have a look anyway. So our input now is 64 milliamps, our 12 volts, which is going into C1, and between C1 and C2 we have our 176 milliamps at 12 volts. The other thing to mention about this is course you don't need to use it as a pulse motor. You can take the coil away, stop the rotor, and you now have the solid state as before. So versatile in that it can be a pulse motor or solid state without any change to the circuit whatsoever. The efficiency in solid state mode is better as well, so we are drawing 72 milliamps at our supply voltage of 12 volts, and we have 216 milliamps between C1 and C2 in what is now our loop circuit. So quite interesting, and I believe will become useful in the future. So not too bad, and simply a matter of placing the coil back there, giving the rotor a spin, and you'll see once again it'll start taking off as a pulse motor, or an electric motor, whatever you want to call it. Alright, thanks guys.